In this lecture, let's look at another important class of trigonometric identities. It's called the sum and difference formulas for sine and cosine. First, let's look at the sum formula for the sine function. It says sine alpha plus beta equals sine alpha times cosine beta plus cosine alpha times sine beta. You see, there's some kind of symmetry here, right? Sine, cosine, plus cosine, sine. All the other sum and difference formulas can be deduced from this one. Now, let's prove this sum formula. Okay, for convenience, I just assume that both alpha and beta, they are acute angles, and I put them in the isosceles triangle ABC. AB equals AC is 1, and I divided A into angle alpha and beta. Okay, let's prove this. Proof. Now, first of all, let's recall. When we prove the law of sine, we have derived the formula of the area of a triangle involves the sine function. So for here, if I have triangle ABC, then the area of the triangle can be calculated by AB times AC times the sine A and divide by 2. Okay, so let's recall. The area of triangle ABC equals 1/2 times AB and times the AC times the sine, the angle A. Right, so this is what we derived before when we prove the law of sine. Okay, so if we plot AB is 1, AC is 1, and A is just alpha plus beta, this one equals 1/2 and sine alpha plus beta. Therefore, sine alpha plus beta, sine alpha plus beta is just twice of the area of triangle ABC. Then the question is reduced to whether we can prove the right hand side. These two things, they add together, is also the twice of the area of ABC. Okay, let's do that. Let me draw a helping line. I draw the height from C to AD, so this is perpendicular. This is why I put SE. And then I also draw B, the height, the perpendicular line from B to the line we extend AD. Okay. So that's what we have, and that's this one I put as F. Now let's connect BE, and then we connect CF. Okay. The reason I'm doing that is just because I want to create those quantities sine alpha, cosine beta, cosine alpha, and sine beta, and then we find a geometric interpretation to see whether the right hand side equals the twice of the area of ABC. Okay, now let's see whether we are able to find these quantities here. First of all, because this is beta, here's 1. By the definition of sine, we immediately get this part of the CE. This one is sine beta. And then this one, A to E, this is the cosine beta, right? And then I have, this is the alpha. And this is 1, so I have the BF is sine alpha. So I get this one is just the sine alpha, so this is sine alpha. Alright, and then AF, if I look at AF, all the way from here to AF, this is just the cosine alpha. So let me put it here. So AF equals from A to F, AF is cosine alpha. Alright, okay, so we have marked the quantity sine beta, cosine beta, sine alpha, cosine alpha on this picture. And the next thing to do is try to connect those things with the area. Okay, let's look at these triangles ACF. Okay, so let's look at the triangle ACF. Now, how do we calculate the area of ACF? So we have the area of triangle ACF. Area of triangle ACF, we can do is the height multiplied by the base, right? So this equals 1/2. The height, that's CE, multiplied by the base, that's AF, times AF. Well, if I replace CE and AF by sine beta and cosine alpha, and this is just 1/2 sine beta times cosine alpha. Okay, good, right? We have sine beta, cosine alpha. This term already appears. Okay. Now, what else? Then let's look at the triangle AEB, the green one. Let's look at the green one. Okay. So then we have the area of this green one. So that's ADE. Maybe let me put this is the black one. This is the red one, and then we have the green one. Okay. Okay. So the area ABE equals 1/2. Again, use the base, that's AE, the AE, and multiply by the height BF. So that's the AE times the BF. Okay. What does AE? AE is cosine beta, right? AE is cosine beta, so that's right here. And BF is sine alpha. Okay, so this equals 1/2 cosine beta times sine alpha. Alright, that's what we have. Now, we need to do is, we want to say, okay, let's add these two things together. So add them together. Add the area of ACF and the area of ABE. Then, which is you add this one and that one together, right? So it's right here. Okay. The question is, now, we already have this one plus this one, which is on the right hand side of the equality we want to prove, and this is on the left hand side. Okay. So the problem is we do to show whether we are able to have that. The area of ACF plus the area of ABE equals the area of ABC. When you look at the picture, right? When you look at the picture, you see, well, there are difference. So ACF is this one plus extra CDF here, and ABE is the ABD but minus this part. If I take the difference, if I have this triangle, so triangle ABE plus the area ACF, right? Everything is in areas, minus the triangle, the whole thing, that's ABC, right? With ABC, what do we have? That one equals CDF, the triangle CDF minus, so CDF minus this BED, right? Minus angle BED. Accordingly, it eventually boils down to the question, if you look at the two triangles, right? If I mark triangle 1, triangle 2, okay. If I mark the two triangles, CDF, BED, do they have the same areas? The answer is yes. This one is indeed 0. Now, why is that? Let's look at BFCE. Okay, so CE is perpendicular to the AD, and BF is also perpendicular to the same line. So here I have this BF is parallel, right? So BF is parallel with CE. This tells us here we have BF, so this quadrilateral, so BFCE, this is a trapezoid. So BFCE is a trapezoid. Okay. Now the point is, if we have a trapezoid, right, these two bases, these two sides, they're parallel, and they have that. Now we connect diagonals. It separates the trapezoid into 4 parts, right? So the point is, these two opposite parts, we say the wing, right? Two wings, they have the same areas. Okay, here's the statement. If I have a trapezoid, So this is trapezoid. Okay, now we connect these two diagonals. Now I have two parts, S1, this is S2. Then we have the area S1 equals S2. The reason is very simple. If you look at this triangle, the bigger one, so we have the bigger one, triangle 1, and then you look at another one, triangle 2. If I look at another triangle, this triangle, okay? Now, the two triangles, they have this one and this one. These two, they have the same areas. Why? Because they share the same base, and also the height is the same, right? If you draw the height, this is the height, and then this one has the height. Okay, so the height, the two heights, they are the same, and they share the same base. So these two triangles, this one and this one, are the same. Now, how you go from that 2 to S1 and 2? So S1 plus this is that, S2 plus this is the green one, is the red one, right? So yeah, basically we have the red one and the green one, the red one and the blue one, they have the same area. Right? So they have the same area. Now, S1 plus this one is the blue one, S2 plus this one is the green one, and that is the common one. Therefore, we deduce the two opposite parts, they have the same area. Okay, now we just apply to here. I have trapezoid BFCE, because BF is parallel to CE, and these two things, the two triangles, they're opposite, just right here, and accordingly, I have the area is the same. Okay, and this proves the area of this plus the area of that equals the total area ABC. Well, it's the area of triangle ABC, and then, of course, we deduce this one, these two plus together equals sine alpha plus beta. We can cancel 1/2 on both sides, and it leads to what we want to prove. Okay, so this proves the sum formula for the sine. Now, let's see other sum and the difference formulas for sine and cosine. Okay, so we have proved sine alpha plus beta equals sine alpha cosine beta plus cosine alpha sine beta. And we also have sine alpha minus beta equals sine alpha cosine beta minus cosine alpha sine beta. And cosine alpha plus beta equals cosine alpha cosine beta minus sine alpha sine beta. And cosine alpha minus beta equals cosine alpha cosine beta plus sine alpha sine beta. 2, 3, 4, they can all be deduced from the first one through various trigonometric identities. So let's see, from 1 to 2, at least, so if we say, okay, I want to go from 1 to 2, at least the formula, we say, oh, we just change beta to negative beta, right? So we just go from change beta to negative beta. And then, you see, if I replace their beta by negative beta, so because alpha minus beta is just alpha plus negative beta. So I change beta to negative beta. Cosine is an even function, so cosine negative beta is the same as cosine beta, so it does not change. But here, if I change beta to negative beta, then sine negative beta is negative sine beta, because sine is an odd function. That's why here we have negative sine. Okay. Now let's see how we go from, we can go from 2 to 3. From 2 to 3, what we can do is we use the trigonometric identity, sine theta, or we say sine pi minus theta equals cosine theta. Let's do it. Okay, so from 2 to 3, we have the cosine alpha plus beta equals, which is sine, that's pi over 2 minus alpha plus beta. And this I can write as a sine pi over 2 minus alpha and minus beta. Then I can just apply this, you can consider this as one angle. So this one minus beta, and we can use 2, right? So by 2, so this equals by 2. This one is the sine. This one is the sine pi over 2 minus alpha and times cosine beta. And then it's minus. So it's minus cosine pi over 2 minus alpha and times sine beta, right? Okay, so we use the trigonometric identity, this one again. We have this quantity, this equals cosine alpha, and then we have the cosine 2 pi minus alpha, this one is sine alpha, and if we combine this together, we just get the 3, right? Equals cosine alpha, cosine beta, minus sine alpha, sine beta, right? And then it's okay, I want to go from 3 to 4. Well, again, formally, you can just let the beta to be negative beta, right? Change beta to negative beta. And then we use the cosine function, even so cosine negative beta is cosine beta, does not change. But if I change sine beta to sine negative beta, sine is odd function, so it's sine, you get negative out. So negative, negative, this leads to positive. Okay. Alright, so the point is, if we start from 1 by use the trigonometric identities, we can deduce 2, 3, and 4. Okay, now, in 1 and 3, let's set alpha equals beta. Set alpha equals beta. And let's see what we can derive. Say in 1, let alpha equals beta. And then we have, and this on the left hand side is sine, you can sine 2 alpha. Let's say both of them we just use alpha. We get sine 2 alpha equals, this is sine alpha cosine alpha plus cosine alpha sine alpha. So the 2 copies of sine alpha times cosine alpha. Okay? So we get 2 sine alpha cosine alpha, and we get this formula, right? Okay. So this is so-called double angle formula for the sine. Now, let's look at cosine part. In 3, again, I let alpha equals beta. This leads to, on the left-hand side, we have cosine 2 alpha. So I have cosine 2 alpha equals, this is the cosine alpha, that's squared, equals that, and then minus sine alpha times sine alpha squared, right? Okay, now, so we have cosine 2 alpha equals cosine alpha minus, so cosine alpha squared minus sine alpha squared. If we use the identity, that's what we call that, if we have the sine alpha squared plus cosine alpha squared equals 1, we can replace either sine alpha by cosine alpha or cosine alpha by sine alpha. And let's say we go with cosine alpha, and that is what we get is 2 cosine alpha squared minus 1. So if we go with, or if we go with the sine alpha, and that we'll get is 1 minus 2 sine alpha squared, and this is another double angle formula. It's on the cosine part. Okay, so these two together, cosine alpha is 2 sine alpha cosine alpha. Cosine 2 alpha equals this, or that, they together, it's called the double angle formula. This double angle formula. Okay. For 2 sine and cosine. Next, let's see some applications of the sum and difference formulas. Example 1. Find the sine value of 15 degrees. Here I use the unit of degrees. We already know the sine and cosine value of some special angles like 60, 30 and 45 and also 18, 36 and 72. The idea is to see whether we are able to write 15 as the combination of those special angles, and then you can use the sum or difference formulas or the double angle formulas. Alright, here we have two ways to handle 15. One is use the difference formula. So clearly we know 15 equals 45 minus 30. Or we use the double angle formula. Same as twice of 15 equals 30. That is also a special angle, right? Okay. Alright, so let's use the method 1. Let's see the method 1. So method 1, we use the difference formula. As I said, so 15 degree equals 45 degree minus 30 degree. And then, if we recall the formula, sine 45 degree minus 30 degree. Now, sine alpha minus beta equals sine alpha times cosine beta and minus cosine alpha sine beta. Alright, so this one equals sine 45 degree times cosine 30 degree minus cosine 45 degree times sine 30 degree. Okay, let's plug into here. So we have, this is square root 2 over 2, that's sine. And cosine, this is square root 3 over 2, that's cosine 30. We need to memorize sine and cosine values of those special angles. Okay, and then this minus, so cosine 45 is also square root 2 over 2, and sine 30 is 1 over 2. Now, if we combine them together, we get the sine value, so it's 4, the denominator 4, and the numerator is the square root 6 minus the square root of 2. This is equals, so this one equals sine 15. This one is sine 15. Okay. Alright, now let's look at another method by using the double angle formula. Method 2. We use the double angle formula. Okay. Let's recall that. Right, so here we are using sine. We know the cosine 2 alpha equals, it's 1 minus 2 sine alpha squared, right? Okay, so of course from here we just get sine alpha squared equals 1/2 1 minus cosine 2 alpha. Alright, so here our alpha, so we just left alpha equals 15 degree, and then 2 alpha is 30. So we have the sine 15 degree squared equals 1 minus, this is cosine 30 degree, right? 30 degree, and this equals, now we replace this by square root 3 over 2, and write out, we'll get this one equals 4, and 2 minus the square root of 3. Okay. So we get sine 15 degree equals 2 minus the square root 3 over 4. And then we just take the square root. Since sine 15 degree is positive, 15 is the accurate angle, so I can take the square root. Right? Take the square root, so this implies we'll get, I take the square root on both sides. So I take the square root. This equals the square root of 2 minus 15, 3 over 4. And you can check, when you first look at this, you might think, oh, they are very different. But if you check, you find these two things, they are the same. If you take the square of this, you get the 2 minus the square root of 4. So these two things, they are actually the same. Let's look at the second example. This is a past question from AMC 12A. The problem says, say we have two angles AB. Sine A plus sine B equals the square root of 5 over 3. Cosine B plus cosine A equals 1. And based on these two equalities, what is the value of cosine A minus B? Okay. Now, if you recall, the difference formula for cosine A minus B. We know cosine A minus B equals cosine A cosine B. Okay, here's plus. So this is plus sine A times sine B, right? Therefore, if I'm able to figure out cosine A cosine B, sine A sine B, then I will get the cosine A minus B. Okay. The question is, how can I get cosine A times cosine B? How can I produce sine A times sine B? For that, let's go back to these two equations, right? Here I have these two equalities. Now I have sine A sine B. You see how I get sine A times sine B? Well, obviously, if I take the square on both sides, and then I'm going to get the mixed term. If I take the square on both sides of this, I will also get the mixed term cosine A cosine B. Right, so let's implement that. Let me put this one as A and this one as 2, right? Equation 1, equation 2. Now for this identity 1 implies I take the square on both sides, so I get sine A plus sine B squared. This equals, let me write out. This one is sine A squared plus the twice sine A sine B and plus the sine B squared, and this equals 5 over 3, right? It's 5 over 3. Then let's take the square of the second equality. So 2 implies I take the square on both sides, so cosine A plus cosine B squared equals the cosine A squared plus the twice cosine A cosine B, and then plus the cosine B squared. This equals 1. Now, our goal is to want to generate the two things add together, right? Then obviously, what I should do is I just add together, add these two together. I'll get add this, add this, add this, add this, add this. Now, the point is, although here we have the terms like sine A, sine B, cosine B, but if we recall, these two things add together equals 1, and these two add together is also 1, and therefore I derive, we'll get 1 plus, that's what we want, so twice, it's cosine A, cosine B, plus sine A and sine B, and then plus 1 equals, this is 1 plus 3 over 5, right? And therefore, we can remove, so 1 cancel with 1, and then you move another one to the other side, and this minus 1, right? Equals it's 2 over 3. So we get twice of cosine A cosine B times sine A times sine B equals 2 over 3, and then we just divide 2 on both sides, and finally we derive these two things add together equals 1/3. Example 3. Here we have a trigonometric equation that appears in a past AMC 12 problem. It says, say we have angle x that's between 135 degree to 180 degree. Okay, so here we are in the unit of degrees. If we know sine x plus cosine x equals cosine x sine x, right, so this is the trigonometric equation. And the question is, then what is sine 2x? Okay, so when we look at this problem, you see how I connect sine 2x with this equality. Well, this equation, we say this equation. Now, sine 2x, we know by the double angle formula for a sine function, we know sine 2x equals sine 2 sine x times cosine x. Therefore, what we need to do is we need to derive information sine x and cosine x from this equality. We already have cosine sine x on the right hand side, then we just need to look at the left hand side. Now, this is similar to the previous example we did. You see, if I take the square on both sides, I'm going to get the mixed term is exactly sine x cosine x times 2, right? So let's do that. We just take the square on both sides of this equation. So let me put this equation as equation 1. So from 1, I take the square. We'll have the sine x plus cosine x squared equals cosine x sine x squared. Okay. Now, sine x cosine x squared, we just write out. This is sine x squared plus twice sine x cosine x, right? And then plus cosine x squared equals on the right hand side. That's cosine x, again, just leave it here, squared. Now, the point is, you see, we already have cosine x, sine x, cosine x, sine x, that's just 1/2 of the sine 2x, right? What are the others? We have sine squared plus, we have sine squared plus cosine x squared. We know the two things, if you add them together, it just equals 1, right? We have sine x squared plus the cosine x squared, this is 1, so this just equals 1. Therefore, we basically just get an equation of sine x and cosine x. If I do it, let's say if I let the a equals sine 2x, then this one just equals a over, this is a over twice, and a over 2, and this is just a. You see, we get the equation of a, so we get a quadratic equation. We get a 1 plus a equals, and that is the a squared over 4, right? Now, this is just a quadratic equation. We'll have the a squared minus 4a minus 4 equals 0, and then by the quadratic formula, we can get the a equals, here is 4 and a plus or minus the square root of 32. If I simplify this, I get is 2 plus or minus the square root of 2. Now the question is whether both values are valid. Here we have two options, 2 plus the square root 2 or 2 minus the square root 2. Okay, now what we need to do is we need to examine the sign of is plus or minus for a. Because here we have a range for x, so if x is between that, we get a 2x, so that implies 2x is a 270 to 360. We know that is on the fourth quadrant. Okay, if you recall the sign of the Yifeng sign, so on the first quadrant positive, the second quadrant positive, the third quadrant inside, the third quadrant is negative, the fourth quadrant is also negative. So here for what I have, therefore what I have is this one is less or equivalent to 0, right? So less or equal to 0, and that implies we can only have the negative one. So a shall be equals, there's no positive, is negative. And that is the value of sine 2x, it's a minus the square root of 2. Example 4. This is also a past question from AMC 12. The problem essentially asks you to show that if for x and y, if both of them are within this range from 0 to pi, right, this is in radians, then we have a sine x plus y is less or equivalent sine x plus sine y. Let's prove it. Instead, in fact, let's prove a more general inequality. So forget about x and y incident type. Let's see this. Proof. We use the sum formula. So we have sine x plus y equals sine x times cosine y and plus cosine x times sine y. This is always true, right? This is sum formula. Now let's take the absolute value on both sides. From here we implies if I take the absolute value of x plus y, that equals the absolute value of sine x cosine y plus cosine x and sine y. Now, we use a triangle inequality. So here this is less or equivalent. This one is less or equivalent. Here we use the triangle inequality for absolute value. This is so-called triangle inequality. If I have two numbers a, b, so here a and b are two real numbers, this just means the collection of real numbers, then the absolute value of a plus b is less equal to the absolute value of a plus absolute value of b. Now the proof of this is very simple, because if a and b, if both of them are positive, you have equal sign. If both of them are negative, again you have equal sign, because the absolute value of a negative number is negative, negative. This is negative, negative, this is also negative, negative. Now, the situation when you have strictly less than is they have the opposite sign. A is positive or B is negative. A is negative or B is positive. Then here you have the cancellation, right? As part of it cancelled. But here you don't, right? So that's why it's strictly less than. Okay, now so we use this triangle inequality. By that implies this is less equal to the sine x times cosine y and plus the cosine x times sine y. Then we have this part equals the absolute value of sine x times the absolute value of cosine y, and then we plus the absolute value of cosine x and the absolute value of sine y. Okay, now the point is, for cosine y, regardless is when you take the absolute value, so regardless is positive or negative, it's always between -1 and 1. Therefore, if you take the absolute value, this one, the whole thing, this is non-negative, but it's less equal to 1. Similarly, for cosine x, it's always between -1 and 1, so when you take the absolute value, this quantity is between 0 and 1. Therefore, when you combine, so this is no greater than 1, this is no greater than 1, then the whole thing is less equal to the absolute value of sine x plus the absolute value of sine y plus the absolute value of sine y. Okay. Alright. If we combine, so this is sine y. Okay. Now, if we combine, as a summarize, we have this is less than that. So what we derived here, what we have is sine, the absolute value of sine x plus y is always less equal to the absolute value of sine x plus the absolute value of sine y. Now this is true for every x and y. So this is true for all x and y. They are real numbers. Okay, for our situation, if I have the x is between 0 and pi, right? So in this case, so from here we derive, if I have the x and y, they belongs to 0 and pi, we have the sine x and sine y, they are both non-negative. Then from here I derive the sine x plus y, the absolute value is less equivalent. Just the sine x, okay, plus sine y, but this is both of them are negative. This just equals sine x plus sine y. So I get the absolute value is less equal to sine x plus sine y. Then absolute value of course is always no less than the sine of x plus y. Right? So this one is always no less than that, right? Because the absolute value of number is always no less than the number itself. And therefore I get this is less equal to its absolute value is less equal to sine x, sine y. That is exactly on the right hand side. Example 5. Here we have two given numbers a and b. They are not 0. We want to find the maximum and the minimum values of the function f(x) equals a times cosine x plus b times sine x for all x in the collection of real numbers. Now, of course, because the function is 2 pi periodic, it's equivalent to finding the maximum and minimum when x is between 0 and 2 pi. Alright, so here the point is a and b, they are fixed. Okay, so how should we do that? If we have learned calculus, one straightforward way is to take the derivative and find the 0 and then to identify the maximum and the minimum values. Here we are going to look at is more elementary approach without using the calculus. Okay, so let's see how we do that. I'm going to rewrite the solution. Okay, I'm going to rewrite the expression of f(x) so that it's converted in a form we can use the sum formula. Okay, so I have the fx equals the square root of a squared plus b squared, and then the inside we write a over the square root of a squared plus b squared times cosine x, and plus b over the square root of a squared plus b squared times sine x. Now the point is that when you look at these two quantities, a over the square root of a plus b squared, b over a squared plus b squared, and I claim, because these two things, they add, when you take the square, when you add them together, as if I have a over the square root of a squared plus b squared, this squared, plus b over the square root of a squared plus b squared, you get a 1. And therefore, we are able to find a theta. So there exists a theta. So we are able to find an angle theta such that this one equals sine theta, and this one equals cosine theta. So you see, when a and b, they are positive, this is just Pythagorean theorem, right? So if a and b, they are positive, what you have is this, okay? This is say a, this is b, this is the square root of a squared plus b squared, then my theta is just this one. So this is angle theta, right? We put it in a right triangle. We have the original definition of sine theta, so that's how we get theta. And therefore, this one can, it's in the form of the sine theta and cosine x and plus cosine theta and sine x. And this is exactly the form of the sum formula, sine, cosine plus cosine sine, and this one equals the square root of a squared plus b squared, and this sine theta plus x. Now, the theta is fixed, right? It's provided by the cosine sine value, or if a be a positive, it's just within this right triangle. Okay, now regardless what x is, right? This value is always change between -1 and 1. Right? For example, if theta is pi over 2 minus theta, you get sine pi over 2, which is 1. If x is like 3 pi over 2 minus theta, you get sine 3 pi over 2, which is -1. Okay, but regardless what, it's always between -1 and 1. Accordingly, I get the maximum value of f. So what is f? So f will be less equal to the square root of a squared plus b squared, and it's bigger to negative the square root of a squared plus b squared. Okay? So the maximum value equals the square root of a squared plus b squared, and the minimum value of this equals negative the square root of a squared plus b squared.